Good morning to everybody, and I would like to thank the organizers for giving me the opportunity to speak at this nice workshop. I will concentrate in this talk on the effects of vibronic coupling, of vibronic dynamics, on the multipolar interaction in magnetic insulator. So physics begins with Hamiltonian. The essential interaction which we need is the one which describes multipolar ordering. So this means that we have in the space of localized magnetic orbitals, we are speaking about magnetic insulators. We have intrasite interactions we take into account. We take into account intersite dipole-dipole, magnetic, electric dipole, and other interactions. And then we take into account the electron transfer between sites, which describe, for instance, the Anderson superexchange. And this is a conventional description when we don't need to take into account lattice effects. But then, because we have orbitally degenerate sites, we need to take into account also vibronic interaction, Jahn-Teller effect, which always takes place. And this Jahn-Teller effect is described in terms of the local distortions, which can mix the states, localized states on each side. So these are examples of local distortions. So these are our metal sides. So these are the atoms around. They distort in symmetrized, corresponding symmetrized form, and induce mixing between the local orbital or local states. And because of this, we also have to include the entire phonon part, because the local distortions, they expand into phonons via the Van Vleck coefficients. So this is a known thing. So now we want to see what will be the effect of this lattice in the weak Jahn-Teller coupling limit. So when this electron phonon or vibronic interaction is weak. So we do a usual transformation, which we usually do when we obtain, for instance, the usual multipolar interaction. So we do a unitary transformation which remove the transfer part, electron transfer interaction. And because we suppose that our vibronic effects are weak, we do the same with the vibronic part. So this is a standard tool. And what we obtain, so these are usual terms, and these are unchanged. It appears the electronic multipolar interaction expressed via these multipolar operators. And then the Jahn-Teller part will give us also a kind of quadrupolar interaction. Where here the gamma are already the irreducible representations which correspond to the Jahn-Teller active mode, local modes. And they introduce some quadrupolar coupling. And this is the coefficient describing this quadrupolar coupling. It contains the vibronic constants and some quantity, which is a key quantity here. It mediates the interaction between different sides. So it is clear that if you have, say, no vibration coupling between sides, this quantity will be zero because, yeah. So this is how it's expressed. I wrote this expression just to show that, and this is a standard thing which you can obtain from the DFT calculation of phonons. You obtain the phonon spectrum, you obtain the, say, polarization vector and frequencies, and you can calculate this lattice gain function. And then you calculate easily these mediation factors. Yeah, you can express these effective coupling constants, phonon-mediated coupling constants, via these Jahn-Teller energies. Jahn-Teller energy is this quantity. So this zeta for on one side is the inverse of the square of the frequency, effective frequency. So this is Jahn-Teller stabilization energy. And you can express the coupling between different sites, phonon-induced, via these Jahn-Teller energies and this such kind of function, which we call a mediation function. And if you have no dispersion of phonons, this part disappears. So we have, this is natural. So we have uncoupled, elastically uncoupled centers. So how important are these effects? First, we consider an example of uranium-O2, very known. So this is a fluoride structure. So these are the active distortions. These are calculated by crystal field. It was a long time ago, the vibronic constants. So we are in the ground, multiplet is of gamma 5, threefold degenerate. So these are calculated by DFT, the elements of the zeta matrix, which enters in the definition of the coupling. What we see is that diagonal, they are by one order of magnitude larger than off diagonal for this say lattice. And these are calculated, so you know the Jahn-Teller energy for these two kind of modes, they are the most important. And we obtain the phonon-mediated coupling constants, they're given here. And these are, by magenta, we show also in centimeters -1, the pure electronic contribution. And what you can see is that phonon-mediated contributions are not smaller. They are, on average, they're even higher than this pure electronic contribution to the quadrupole coupling between uranium atoms. More than that, if you take next nearest neighbor, which usually electronically they don't transmit. Next nearest is just along the tetragonal direction, by square root 2 longer than this nearest neighbor. You see that they are also not negligible. They are also of the same order. So the conclusion is that we have always to take into account. So if you do ab initio calculation, you obtain the electronic contribution to multipolar coupling. You have to include also the phonon contribution. It is of the same order, if not stronger. Another example is the neodymium pnictide. This is nitrogen. It's a rock salt structure. So each neodymium is surrounded by an octahedron of nitrogens. So these are known active distortions of E-type, of T2 type. And we calculated recently, it was 2 years ago, I think, the multipolar interaction electronic between neodymium ions, because neodymium is in the gamma, is in J9-half, atomic J9-half. If you calculate for entire J9-half, you have till rank 9 terms, so you have a huge number of terms, but actually everything projects on the ground gamma 8 quadruplet, and we have to basically all project on this gamma 8 multiplet. You have till rank 3, till octopolar order. What you want to compare, if you want to just match the phonon-induced contribution, this is a quadrupolar path. It is 2, rank 2, so it's this square. So if you see what is the order of magnitude of the parameters here, it's about 1/4 of millieV, it's about 2 wave numbers. So then we do the same calculation for the phonon-induced quadrupolar coupling. We still don't know the vibronic constants. It is quite difficult to calculate. It is not finished, but we can calculate this transmission function to see what part of the Jahn-Teller energy. Jahn-Teller energy is a few wave numbers we expect. Usually it's like that, but we didn't obtain still the numbers. If we see what is the transmittance coefficient, so these are diagonal, and these are intersite. We see that they are even not 1 order of magnitude, but they can be, say, 4 times smaller. So it is 1/4. It is quite large. So if you'll have this is the coupling constant again expressed via this function. So the function itself can be 1/4, this mediation function, transmit the interaction. So if you have your Jahn-Teller energy of the order of, say, 10 wave numbers, you'll obtain here that the coupling will be about 2 wave numbers. So this is not negligible. It's of the same order. So again, the conclusion here is that we have to take these things into account. In principle, it is not complicated. The following calculation for this simple lattice is the routine stuff. And you have to calculate also the vibronic constants. These are usually by Benicio calculations. So now, is it orbital or vibronic order? So our wave function on sites, localized wave function, because we have included lowest order the electron phonon coupling, it will admix some excited states, not excited states, so opposite, say, to gamma states, another components of the degenerate manifold, and some phonon with some one phonon excitations. So if you will analyze this, so this one phonon excitation and one Fleck coefficient, if sum up over k, will give you effective vibrational state of the gamma type, active gamma type. So this is more clearly seen if you consider a simple molecular E problem, and you do the same thing, you obtain such a wave function. In the case when we take into account Jahn-Teller coupling. And what we see is that the addition to a pure orbital is due to this coefficient. So the parameter which enters here, which we denote by k gamma, defines if you have weak Jahn-Teller coupling or strong Jahn-Teller coupling. So if this ratio is small, so Jahn-Teller stabilization energy to frequency quantum is smaller than 1, then we have the limit of weak Jahn-Teller coupling. So we can estimate this thing, this effective omega gamma we obtain by inverting the zeta matrix, and this is what we obtain for uranium O2 and neodymium N. So this is the ratio which you obtain. So we are definitely in the weak coupling limit. And then we can say that we have just the orbital ordering or orbital interaction on sites. We can forget about vibronic admixture. The only thing, these vibronic Jahn-Teller effects, they give additional terms into a pure electronic multipolar, say, Hamiltonian. But is it this the situation which is typical for magnetic materials? And here is just a kind of, say, I took some examples from literature, and what we see that for textbook example like manganites, we obtain that Jahn-Teller is much stronger than effective H omega. So we are definitely, or for copper, it is about 1 order of magnitude stronger. So we are definitely in strong coupling limit. The same you can say about fullerenes. They are on the limit of intermediate strong Jahn-Teller coupling. Yeah, these materials, they are also on weak Jahn-Teller limit, approaching the intermediate, something like that. So the situation is that we have many examples of strong Jahn-Teller coupling on sites. In this case, the effect of multipolar interaction is different. So how we should understand these effects? First of all, how look the solution on one single site if you have isolated site. If you have, for instance, E problem, yeah, Jahn-Teller problem. It's twofold degenerate term with twofold degenerate orbitals. So this is the adiabatic potential surface. This is the point of degeneracy. Q theta Q epsilon are distortions. We can describe in polar coordinates. The lowest spectrum corresponds to rotation along the trough. This is one-dimensional continuum of minimum. And we have two motions. One is rotation along the trough, so the radius of trough is not small. It is of the order of vibronic coupling over omega E. It is not small. And we have the radial vibration here, just omega E. So this is how look the energy. And these are considered fast system. And the slow system is rotation along the trough because the radius of trough is in principle is large. And of course we did the adiabatic separation. So if you go up to intersect this surface, it will be 4 Jahn-Teller energies. And if this is strong Jahn-Teller coupling limit, we can neglect the non-adiabatic mixing with excited surface. And we have just the dynamics on the bottom. It looks like that. We have a slow system, it's rotation, and radial vibrations in the trough. So this is how they look. And our state now is not just the degenerate orbital state, but the ground state is degenerate vibronic state because it corresponds to J plus minus 1/2, which are degenerate. So orbital degeneracy transforms in vibronic degeneracy. It's only if we localize in one point on the trough, we have a huge splitting, we have non-degenerate state. But if it allows vibronic dynamics, it restores the degeneracy, but this is now vibronic degeneracy. So this wave function is not, it cannot be factorized in a pure electronic part and pure nuclear part. It has here the nuclear, essentially depends on the nuclear coordinate. If you go along the trough, this adiabatic function, this is electronic function. It transforms from psi theta, then psi epsilon minus psi theta minus psi epsilon. So making a rotation, it passes equally from the state's two components of orbital doublet and with equal weight. So on average, they are equally populated. There is no, say, orbital ordering. How to apply it just qualitatively? So we have static cooperative Jahn-Teller effect, when you have static distortions. So when it happens first of all when we have a weak non-adiabaticity on sides. So if you have E-bit problem or TE problem, then the vibronic operators are diagonal. And then what we have, the effect of vibronic effect is just the distortion in some minima. And then you have just phonon, say, oscillation at the bottom of the minimum. In the case, for instance, this is EB Jahn-Teller problem. If you have some gap introduced, then you have vibronic dynamics, you have tunneling states. But if you have strong enough molecular field due to the presence of other molecules, which are also distorting, so it's a cooperative effect, you can localize this state and it becomes just vibration on the wall. In this case, you separate, again, you have Born-Oppenheimer separation of electronic and vibronic motion. Here you have orbital state. And vibrations are just oscillator in the bottom. And then we can say about orbital orderings, and you have static distortions of the order of the minimum in this adiabatic potential surface. But we have another situation when you have essential non-adiabaticity. This is EE problem, for instance. You have HT problem in the case, TH problem. Polarites, you can have gamma 8E problem. When you have continuum of minima in the adiabatic potential energy surface. And then if you have weak molecular field, so the molecules do not interact elastically strongly, of course, due to static field, you have some distortion of the trough. You have a region where it is lower. But if it's not strongly distorted, you still have a dynamics around. And you keep your degeneracy. In this case, you have dynamical, even if they order these molecules, but they order the dynamical states, not the orbital states, which are fixed in one position, electronic state, but the entire dynamical vibronic states. The orbital order is practically suppressed, and the static distortions are very small. They don't correspond to the radius of the trough, because when you average on this motion, the average Q will be very small. So this is a fingerprint of dynamical order. When we have this situation, there are two classes of compounds when we encounter this situation. These are, first of all, fullerenes, alkali-doped cubic fullerenes, and these are D1 double perovskites. Yeah? So the fullerenes, these are fullerene molecules, which can, say, crystallize in two BCC and FCC. If you have cesium-free C60, this is the most famous representative, but you have also expanded fullerized when you put here NH3 ammonia molecules, and then it expands and say this another class. So yeah, it's just by passing cesium-free C60, it is very close at ambient pressure, very close to the verge of Mott Hubbard insulator, and it gives the highest temperature, superconducting temperature, about 38 degrees. Basically, it's high TC superconductor. But if you apply pressure, it passes through this Mott Hubbard transition, become insulator, and this is what we want to describe in this case. All other expanded fullerized, they are Mott Hubbard insulator already for ambient pressure. So to describe this, first, what is the entire effect on each fulleride? You have the highest, lowest unoccupied is T1U free-fall degenerate. When you put alkali atoms, it is docked by one electron or few electrons, and you have the entire effect interacting with modes, five-fold degenerate modes, Hg modes. So this is how look these orbitals, and these are the modes. And this is the vibronic Hamiltonian. So you have the interaction of these three. They are isomorphic to the pi orbitals, atomic pi orbitals, these three T1U. So you can describe by these indices. And we have 8 these modes. So they have been, the vibronic constant have been extracted from photoemission experiment, and that was done several times. And by the way, by DFT calculation with B-free you can almost reproduce this photoemission profile and extract all vibronic constants, which enters with different Hg modes. But we actually have C60 free minus, because this is a free C60. So in this case, free electrons is like putting free electrons in pi orbitals. You have free terms, H term, P term, free-fall degenerate, D term, and there is S term, which is non-degenerate. The interaction is also between P and D, the entire interaction. Now we first want to apply this model to expanded fullerides. Expanded fullerides, the interaction between them is very weak, and we expect that this interaction will not mix the vibronic states, excited vibronic states. We can formulate the problem only in terms of the lowest vibronic states. And then what is also we proved that the ground vibronic state is basically this determinant of these adiabatic orbitals, the adiabatic orbitals. So it is this. So they move on the trough, three-dimensional trough. So it is not one-dimensional continuum of mean, but it's three-dimensional continuum of mean. You have two radial, if you take one effective mode, two radial vibrations. And this is just a simple spherical harmonics in terms of theta 5. These are nuclear coordinates corresponding to rotation in the trough. Then we say basically we solve this problem. So we have free-fall degeneracy, but this is vibronic degeneracy. For exchange interaction, we obtain a typical Kugel-Khomskii Hamiltonian. So this K and J, these are 9 by 9 matrices corresponding to product free and free orbitals. So this is how the pairs are along free-fall axis, and the momentum is conserved. What is important is that if you analyze this interaction, what we see, due to vibronic reduction, we have these terms K, B, and the terms which are not constant here in J, B, depending on the operator and theta, they are very small. They are much smaller than the constant. So the main interaction is isotropic Heisenberg interaction. And this is confirmed experimentally from susceptibility. And then so the ordering first is antiferromagnetic ordering. When it happens, then we go down. Already the ordering of vibronic states will happen in the presence of magnetic order. When we describe this, we obtain the the ordering of quadrupolar moments. They are like that. So A are, say, vibronic orbitons. This is creation of states, vibronic states, real. It's a real combination. And of course, the angular, vibronic angular momentum average to 0 in these states. And what is ordering is vibronic quadrupolar momentum. What is, we did such a calculation. We compared for one pair the exchange spectrum which you obtain if you take one pair only, and see what exchange spectrum in function of two. We have two transfer parameters. So you have like pi orbitals, you have sigma sigma and pi. So T0 is sigma sigma, T1 is pi orbital. As function of this ratio, you obtain such an evolution of spectrum. If you compare with corresponding Kugel-Khomskii Hamiltonian, it is for T2G1 with the same parameters. You see that Kugel-Khomskii give much larger splitting, and it can be both ferro and antiferro. While in the case of this dynamical vibronic problem for the pair, we have the ground state is only antiferro. So this is completely confirmed by experiment that we have only antiferromagnetism here. Next, we came to recently we considered the same problem in cesium-free C60. The difference is that in cesium-free C60, the C60 balls are much closer to each other. The interaction is stronger, and you have already to take into account not only the interaction between the ground vibronic states, but also to take the excited vibronic states. Well, this is, we did ab initio, so we took this is the vibronic spectrum of C60. This is shown how they split free P, so free T1U free shell, splits in three terms, exactly like an atom, like a nitrogen atom, for instance. But because of strong Jahn-Teller effect and dynamical stabilization, you have the ground state is lowered compared to Hund rule for S state by about 65 milliV. So we have everything develops at this level. Okay, so there are many evidence. And basically we consider the interaction between C60 balls only for these lowest vibronic states. So for expanded polarized, we consider this one. And for this case, cesium C60, we take into account also the five-fold degenerate excited vibronic state. So this is formulated conveniently in terms of multipolar operators, the interaction. So it is defined via operators which arise from these vibronic states. They can be expressed in this way, just symmetrized combination. And this is how looks the interaction Hamiltonian in this case. So again, it has the form of Kugel-Khomskii, but in terms written not of spins or orbital operator, it's in terms of this multipolar operator. This is what we obtain. So for the A15, we have, of course, we have antiferro always, as we discussed. This is the general rule. Again, as in the case of expanded, we have ferro for vibronic quadrupoles. They order in ferro fashion. So you have on all sides, you have the ferro ordering of quadrupole vibronic states. So these are the components of these states. In the case of FCC, for this type of ordering, the calculations show that we have two types of multipolar different. On the different sublattices, we have different multipolar order. They are not just of opposite sign, because this last component is of the same sign. So it is such kind of interesting. This is ordering of vibronic moments. It's not orbital ordering. It is zero orbital ordering. this vibronic moment. So what orders is the vibronic states. So these states which rotate, this is also a state. And these states, they are somehow ordered. They are definite values, population, say, on sites. A similar physics basically takes place in double perovskite. I will not concentrate, so Naoya Iwahara will give a talk on Thursday. He will speak more about that. So what we have here, the ground state is gamma 8, we know, and we can, it is by symmetry can be written like pseudo-orbital and pseudo-spin. So pseudo-orbital is like an EE problem, interacts like EE, and you have again a trough. Because the trough is, you have lambda is not infinite, the interaction, this produce some warping of the trough. And what you have a kind of hindered rotation. So the ground state is a doublet, plus minus 1/2 vibronic doublet. But next vibronic doublet splits in A1 and A2, and this A approach this ground state doublet. So you have to consider 3 states. So these are Kramers doublets. These are vibronic states which rotate. These are hindered rotation. So then this is a calculation of the phase diagram. In different diagrams you have spin ordering, you have ordering of these vibronic quadrupoles. I will not concentrate on this. Now I will speak talk. So the conclusions, what is the main conclusions? So there are situations with dynamical Jahn-Teller effect on sites, and this gives rise to a new cooperativity, is dynamical vibronic order. It's not orbital ordering, it's dynamical. So the science is small static and distortion and strongly reduced orbital anisotropy when you have these dynamical effects. So they are realized in a system of non-essential vibronic non-adiabaticity. So this should be Jahn-Teller problems which give you a trough, multidimensional continuum on the minima. Implication for the multipolar ordering is that in this case, yes, you have the same multipolar interaction, but between vibronic states. If for some reason you have localization, strong localization in a trough, then you have immediately the splitting, huge orbital splitting, and you have non-orbital, non-degenerate ground state, and then you don't have a multipolar coupling. So in this sense, the dynamical vibronic effect, it introduces a multipolar coupling between the sides. And I would like to take the opportunity to pay tribute to the memory of our distinguished colleague, Kugel-Khomskii, who recently passed away. So we all know Neil, probably all of us. Yeah? So he was a brilliant scientist. He is largely considered the founder of the domain of orbital effects and magnetism, and Kugel-Khomskii Hamiltonian. And he was also a brilliant person who influenced many of us by his insightful ideas. Thank you for your attention.